In the last section, we talked about finding a series solution of a differential equation around an ordinary point. In this section, we're going to talk about finding a series solution around a singular point. And it turns out this method is only going to work for a regular singular point. Okay, so if x equals x naught is a regular singular point of a second order linear differential equation, then the theorem says there's at least one solution of the form sum constants x minus x naught to the n plus r, where r is a constant to be determined. So two important things to talk about there. First of all, at least one. What that means, since we're expecting to get two solutions of a second order differential equation, is that we'll probably end up having to do something like reduction of order to find the second one, which is essentially impractical to do by hand. And so you'd probably then resort to using computer software if you needed to find both solutions. The other thing that's important to note is that we're used to finding a series solution around 0, x naught equals 0. And so this formula here is really going to be a sum Cn x to the n plus r. And so if you think about how is it different for a regular singular point versus an ordinary point, well, we just have a plus r. In theory, that's the only difference. I do want to kind of compare and contrast the two options, though. So we have our ordinary point and our regular singular point. And again, for the sake of my own sanity, I will be assuming that we're talking about x equals 0 in both cases. So for an ordinary point, our initial guess was y is equal to a sum from 0 to infinity, Cn x to the n. And our y prime was a sum of Cn times n times x to the n minus 1. And we said since the first term is actually going to be a 0, really your sum is going to start when n is 1. And then the same game when you take the second derivative, your sum is going to actually start at 2 since we have an n and an n minus 1. On the other hand, when I talk about a regular singular point, the only difference is the n in the exponent turns into an n plus r. And so when I take y prime, we'll have Cn n plus r, and then the power goes down by 1, n plus r minus 1. And our second derivative would have more of the same, Cn n plus r minus 1, x to the n plus r minus 2. The thing that's going to be different, though, other than having an r in the exponent and having a slightly more annoying expression here than just having n's and n minus 1s, is that the reason we were able to change our starting point is that the first term, the n equals 0 term, was just going to give us a 0. We don't yet know what r is, so there's no way to know whether the first term is going to be a 0 or not. So that means that when we're doing a series solution around a regular singular point, all of the n's are going to be n equals 0. So that's another place that is different. So we have two differences, our plus r in the exponent, which is going to then percolate through all the later steps, and then our summation is always the same as opposed to, for ordinary points, it was 0, then 1, then 2. Okay, so this is the form of the solution for a regular singular point.